patient, but which has been done before the patient arrives in the clinics. So it's like every type of data you can think of, from in vitro cells to animal studies, to clinical studies in large patient cohorts. And the idea is to gather all that into mathematical modeling, which we call, sometimes we call them PK/PD modeling, sometimes systems pharmacology. And the idea is then to address the challenge of personalizing and optimizing the medicine using this type of modeling. So this is what I'm saying right now. So the tool that we are going to talk about right now is about the modeling to address the challenge of optimizing the treatment. So as you can see, the idea is to design this type of mathematical model here that will take into account the patient data. Okay, here you put is the man or a woman, something like that. Is the tumor mutated for some particular genes? And then this model, hopefully, will give you the optimized treatment for this particular patient. And the way we want to address that, or the way we want to design the model, is by integrating any type of data that is relevant in any system. So here I put in vitro data, so for instance on cell cultures. Here you can see a petri dish. Maybe some of them are familiar. Actually, how many people have ever seen a petri dish in the lab? Can you just raise your hand? One? That's it. So just one in the room? I mean, how many people have ever been in a lab, in a wet lab? One, two? Don't be shy. 4, 5. Okay. Okay, so you are mathematicians, I guess. Like most of you are mathematicians. That's it. No, it's good to know because I don't know you, you don't know me. Cool. Okay, so yeah, so in vitro, so I suspect nobody has ever been to animal facilities, like mouse facilities, then probably not. No. Okay, so we also have sometimes we need actually to do experiments on mice. And finally, we can use cohorts of patients, so clinical trials, which can be used to address the optimization for a specific patient. Okay, so let's start by some definitions. So what do we mean by pharmacokinetics and pharmacodynamics? So first, pharmacokinetics is what the body does to the drug. So when you take a pill, when the drug enters the body, it will be challenged in several ways. It's specifically called ADLE, here. ADLE. So it stands for absorption. So the drug will, if for instance you take a pill, the drug will be absorbed from your intestine to the blood. Then distribution. The blood will distribute drug throughout the body, but will not necessarily uniformly. You also have circulation in the blood, and in the blood we have proteins that will bind to the drug and make it inactive. So this is what I represent here. Circulating protein in the blood that will bind to the drug. Then metabolism, M stands for metabolism, so this is the way that the drug is transformed. So it mostly happens in the liver. This is why here I point to the liver. So some drugs, for instance, has to be activated, and usually it mostly happens in the liver. And finally, the last letter is E, is for expression. So the drug is going to be taken away from your body, taken out of your body, because basically it's something that your body don't want at the end, something that the body wants to get rid of. And it happens mostly in two ways, through the kidneys. That's here. Through the kidneys and then through the urine, so it's called renal clearance or renal excretion, and through the intestine. and then you go to the feces. Well, to be honest, you have also all the ways. For instance, when you breathe, you can actually clear some drugs for some particular drugs. Okay, so that's pharmacokinetics, what the body does to the drug. And the second part, so basically when the drug manages to arrive to the target, it's called the pharmacodynamics. So pharmacodynamics is what the drug does to the target, or to the body, sorry. What the drug does to the body. So imagine I'm studying a drug, a cancer drug that wants to kill cancer cells. So the drug will go, or hopefully go to cancer cells, and so the idea is to look at how the drug will induce cell death in the cancer cells. So this part of the study is called pharmacodynamics. So we want to go and see if the drug goes to the particular target. So when I say target, I mean a particular protein that is targeted by the body. And basically this will have physiological effects. And this is what we want to study. So it could be in terms of response, sometimes we call it response, effect, action, activity. And basically, depending on the drug, it will act on any system. So I have here listed several large systems that could be targeted depending on the disease, depending on the pathology. I guess that's not exhaustive. So this is for the definition. So now let's move to the modeling very briefly. I made like a history, like in one slide history of PKPD modeling, well, in my view. So it all started with a mathematical model, which were non-physiological, which are also called compartment models, and that's the first one here. When I say non-physiological, I basically mean that the compartments do not represent a physiological entity. So it doesn't represent an organ, it doesn't represent a cell, it doesn't represent a protein, nothing. It's just a compartment, so a mathematical variable that is here to represent the profiles that you see in your data. But the variable itself doesn't stand for anything like a concentration in a particular organ. It's just a concentration which is not physiological. Then the second more detailed way of modeling PKPD arrived actually a bit later, and it's called physiologically based PKPD modeling. So it's this type of modeling. Maybe you have already seen this type of diagram. So how many have ever seen this type of diagram? Can you raise your hand? Just to see. Okay, you got it. You're in school pharmacy, right? I guess you have seen. Any other people? Raise your hand. Nobody? Okay. So here you have the blood, the arterial blood, and here you have the venous blood. So the blood flows mostly from there to there. And in the middle you have all organs, or relevant organs, and not all of them. And this is called whole body PKPD, or physiologically based PKPD. And I'm going to say a bit more about this in a minute. And the last, which is the one the most of interest to me, the most recent, is called systems pharmacology, and it's where we go towards the molecular or intracellular scale, where we actually look at the reactions of the proteins in the cell. So and also in the cell, and also in between cells. So we are at the scale of the cells and at the scale of the intracellular compartment. So what we're going to talk about today is basically, that's the outline. So I will go very briefly with some reminders about the dynamical systems. Like it's going to be super brief, just to make sure that everybody has the same vocabulary. And then I would like to present the way that we usually do systems pharmacology projects. So going step by step from the biological question to the solution with the modeling. And then the third part would be about a real-world example, because here the idea is to actually have an impact on patients. And I will show you how we can actually optimize therapy in the context of the overexpression of SAR, which is an oncogene so a protein that is overexpressed in the case of cancer. Okay, so very briefly, so all systems that I'm going to talk about are ordinary differential equation system. So you can write them in vector form like this. And basically, we are looking for solutions that were X is the solution that satisfies one. And so the idea is that for all the systems I'm going to show, you have existence and uniqueness of the solution, provided that you actually give the initial condition excellent. So that's super simple. I guess that everybody got this. Okay, so existence and uniqueness for all systems. So we are going to be interested not only in QNS, but we also are going to be interested in equilibrium, but we are also going to be interested in transient dynamics. I'm going to talk about it later. So equilibrium are defined as the system being set to 0. So x dot or f of x is equal to 0. And then we are going to be also interested sometimes in stability of the equilibrium. So here I made maybe I will just draw. So imagine you have x dot x. Imagine your system is like this. So x is on the y-axis, f of x is on the x is on the x-axis, f is on the y. And imagine that you have actually something like that. So here you have 3 equilibrium, because here you are expressing the f of x equals 0. Yeah? And then for the equilibrium, you just want to see whether or not they are stable or not stable. So a stable equilibrium would be an equilibrium that will attract all trajectories. If you are close to the equilibrium, you are attracted by it. So that's the case of actually this one, the one in the middle. And how do you see this? Because when you're around here, f of x is positive. And remember that f of x is also x dot. So basically you go in that direction, and here f of x is negative, so you go in that direction. So basically you are attracted. If I start somewhere here, I will be attracted to here. So this one is stable. So if I put it maybe, so this is stable. And now if you do the same trick, so now you are around here, so close to this equilibrium. Now the flow is still going that way, so you are basically moving away from the equilibrium. And here again, f of x is positive, so meaning that you are going in that direction, x is increasing. And so here, as you can see, this is going to be unstable, because basically when you are close to the equilibrium, you are moving away from this. And this is the definition of unstable. And it's the same for this one. Okay, and the last thing I wanted to say was about bifurcations. So some of you may have some courses on them. I don't know how many actually studied bifurcations before. Nobody? Yeah, cool. Okay, you have that. Okay, cool. So basically here I haven't introduced parameters, but you can have systems where you also have parameters. So your system will also depend on parameters. Which are equals theta. Okay. And value of theta, so theta is a vector, okay, you can transfer over vector. But depending on the value of theta, your equilibrium can actually change. The number of equilibrium, the stability of the equilibrium can change. And basically, whenever you have a change in the equilibrium due to a change in the parameter, it's called a bifurcation. So let me give you an example. So let's say that you have x that equal f of x of theta, and now your example, the example is as follows. So f of x is equal to x squared minus theta 1. And you can actually draw this in the same way that I draw this, I can actually draw that. As you can already see on the picture, the drawing will depend on theta 1. So if I have, sorry, I put the next. Well, anyway, so if I have theta 1 equals 0, I'll get this. And as you can see, I have only one steady state because I cross x equals 0 only 1. Okay? So this is positive, so I go in that direction, and this is positive. This is so because what I want is the other one. So what I want to do is when I actually put theta 1 is positive, sorry. Then I want the curve will go. Oh, this is really not very useful. I'm going to this. Yeah. Okay, as you can see, I'm just taking this curve and put it down. Okay. And now we have actually two equilibrium. So one of them is stable and the other one is unstable. And on the opposite, when theta 1 is actually positive, then you actually go here, and you don't have any equilibrium anymore. Okay, so that's typically a bifurcation, because basically just changing the parameter theta, you will get different types of equilibrium with different stabilities. Okay, so that's already the end of the reminders of the mathematics. So as you can see, that was really short. And so now let's go to quantitative systems pharmacology. So I will first introduce very briefly the first type of mathematical model I was talking about, which is compartment model. So I will introduce the most simple one, which is the one compartment model. So as you can see, basically, we assume that the body can be modeled as a unit compartment. So this is probably the most simple model you can get. So you have A1, which is actually the body compartment, which stands for the body compartment. And then you put the bracket in the compartment A0. So A0 will be where the drug is, and you have absorption from the A0 to A1. Sorry, I'm going to show you. So if this is where the drug is, then you have absorption to A1, and then elimination, as I was saying, the drug is here. So basically, here you have so three state variables, A0, A1, and A2. So in that case, there are drug amounts, so typically it needs to be moles or gram. And you have two parameters, Ka and Ke, and they are usually, typically, the unit would be the inverse of the time units. So here I put hour minus 1. Here. Hour minus 1. Okay, so now we can think of two different types of administration, drug administration. So let's say that you give the drug intravenously, so directly in the blood. So in that case, you basically say that the drug goes directly to the body. It's like immediate drug distribution. And basically what you do is you don't really have an A0. The A0 is going to be 0 A1. And you have A1 at time t equals 0, which is going to be equal to the dose that you give. And then, okay, I'm going to show the equation for A1. This one. And then the A1 is given by this differential equation, the A1 over dt equal, so the absorption, Ka, sorry, except that for here, we don't have this term because this is intravenous, so here we just have the clearance, so that's minus Ke, A1. So if we have this system for A0 and A1. And if we go for, so this is intravenous IV, maybe I should explain this a bit better. So here, so we are looking at the change of A1 over time, okay? So here, all the drug at the beginning is in compartment A1, and the only thing that can actually happen is the clearance. So it's the So it's the clearance, the thing that I put here above. So basically here A1 is disappearing, this is why you get the minus term, and the rate is just linear. So this is what we call the constant rate, the rate constant, sorry. So this is a parameter, and A1 is just that. So this A1 disappears proportionally to its quantity. So basically when there is no A1 in the compartment anymore, A1 is 0. And it's directly 0, so nothing happens anymore, okay? So this was for IV, but actually this phenomenon actually holds for any type of administration. But let's go to oral administration. So oral is when you take a pill, okay? When I say oral, is when you take a pill. So now you take a pill, the pill is going to be in your stomach or in your intestine. And it will take some time for the drug to reach the blood circulation. For this, we add this A0 compartment. So now we have the dose in the A0 compartment. And we have an equation for A0. So similarly to A1, A0 is going to go from compartment A0 to compartment A1. So it's going to disappear from A0 with the rate Ka for absorption and proportionally to its amount, A0. And A0 can only disappear because all drug is given at time t equals 0. Okay? So then the equation for A1 is a bit different. So now from A1 you will receive some drug from A0, which is the same quantity as the one that disappeared from A0. So that's Ka A0 of T. And as the first one, the drug will also disappear and will be cleared. Ke A1 of T. So the last variable I want to talk about is A2. And A2 is governed by this equation, where it is. But basically, anything that will go out, in both cases, anything that will go out from the compartment A1 will go in compartment A2. Because we don't want to lose any matter. Of course, in terms of initial conditions, there is nothing in A2 at the beginning. So A2, as you can see, is really the last compartment, and sometimes we don't even. Sometimes it's called a sink compartment, in the sense that the matter can only go there and will stay there. So the matter is a bit lost for the system. The sink compartment. Any questions?
In the first kind of document situation, how can it be figured out?
How is that process?
Do you mean injection?
Yes, it's injection directly in the blood. Yeah. And as you can see, the heart will immediately help for distribution of life throughout the body.
But even injection will take some time.
Yes, but related to the time of the drug elimination, because eliminating a drug can last from a few hours to a few days, and drug distribution will occur in a few minutes. So yeah, this is why you are right in the sense that it's an hypothesis, it's an assumption. I mean, it's an approximation. Yeah. Other questions related to compartment modeling? Okay, let's go to the next one. To the next slide. Okay, so the next type of mathematical models are physiologically based models. So as you can see, they are derived from the physiology of the body. So they are typically this type of structure for the PK. So remember, the PK will be how the drug is distributed and transferred through the body. So we have a compartment. Sometimes we only have one compartment. Here we have two compartments for the blood. So the arterial blood and the venous blood. So this one is basically coming from the heart with plenty of oxygen, and this one is basically like oxygen. And you have here you can put whatever you want in the middle, basically. So it will depend on the biological question that you ask. You can put so usually at least we do have the liver, because the liver is important in terms of drug metabolism. So which is why it's at the top here. We also have the intestine whenever the oral dosing is wanted. But as you can see, whenever it's IV here, intravenous injection, we go directly into the blood. So as so the equations are close to actually the compartment modeling, except that now the variables are concentrations in each compartment. So they do have a physiological meaning. You can actually measure them, okay? If you take some cells of the liver and then scratch them, and then you can measure the concentration of the drug, and this is exactly your mathematical variable. And in terms of equations, so this is linear transport related to the flow. Sometimes it's not obligatory, it's not mandatory, but sometimes people actually use the flow. So those Q values are the blood flow that goes through the organs. So it's a measure of the volume of the vasculature of the organ, and in a way it's also a measure of the volume organic. And basically the transport will be linear with this blood flows, Q values. So that's for the PK. For the PD, it's not that detailed. So for the PD, we are looking at modeling the response to the drug. And so the typical model that a lot of pharmacologists use are the Emax model, which is this one, written here. So let's say that you are interested, for instance, in the effect of the drug in some organs. So let's say that you have, I don't know, some effects, for instance, in the intestine. So here, C, this C here, is the concentration of the drug in the intestine. And then you want to model the effect of drug in the intestine, and this is called the response. And then you have two parameters, this Emax and the EC50. And sorry, you have three actually. And this exponent here, the gamma parameter. And your response will look at this. So concentration on the y-axis, sorry, on the x-axis, sorry. Concentration on the x-axis, response on the y-axis. And you will have this type of S-shaped curve. So if so and basically, so your gamma will tell you about the stiffness of the curve. When gamma is really high, you will be close to a square. I'm going to draw this. When gamma is super high, you are close to a step function like this. Okay? And on the opposite, when gamma is close to, for instance, close to 2, you have something which is less stiff, like that. So the green one will be for super high gamma. And I'm sorry, there is a mistake. The numbers are not good here. Don't look at the numbers. Okay, so that's it for the compartment models and for the physiologically based model, PBPK. And that's what I wanted to say. So now let's go to the third type. So do you remember which was the third type? The third type of the models I showed in the introduction slide. No, nobody? You have it? No? Quantitative systems pharmacology. The one at the molecular level. That's where I want. That's clearly what I would like to talk about in detail. So quantitative systems pharmacology, first of all, you can just have a look at when the terms actually appeared. So here, this is a research of a number of articles that were published in the website PubMed. So PubMed is the main website for biological and medicine publications. And if you go on PubMed, and if you search for the keywords quantitative systems pharmacology, so this is the curve that you get in terms of numbers. And as you can see, the terms actually appeared close to 2011. Okay, so this is actually really recent. And then it grows exponentially since then. So the idea is to go at the intracellular level, and let's say that you have two proteins, A and B. A becomes B at some rate K. You can actually model this type of network, and I'm going to detail how. But you can also actually model things at the level of cell populations. As I was saying, you don't have to do only intracellular networks, but you can also do cell populations. And this is an example here that I showed here, where basically you have, so this was a project about brain tumors, and you have a compartment for the blood here, and then you have here several compartments for the brain tumors. You actually have the interstitial fluid where the cells are in, so the fluid that is outside of the cells. And then you have different types of cells. So it could be cancer cells, it could be cells from the microenvironment, like immune cells, for instance. And all inside each box, you can have intracellular networks if you want. I mean, it all depends on what you want to do with the mathematical modeling, but that's the idea. And so why is it interesting to use this type of mathematical model? So the first one is because the variables and the parameters, they do have physiological meaning, so you can directly compare them with your data. And that's really interesting, especially because we know that now we have plenty of different types of data at the level of the molecules, of the proteins, and of the cells. Something also interesting is that probably on the opposite to statistics, this type of approach can handle sparse data. So if you have missing data, or if you have drug exposure schemes which are inconsistent. For instance, let's say I put my drug for 100 milligram for this patient and 200 milligram for those patients. This I can handle it with this type of data, which is something that is less easy when you have statistics, for instance. And basically, at the end, what you have is sometimes we call it now digital twins. Maybe you have heard about this. So the idea is that you have an in silico representation of your system, and you can actually have ideas about the mechanisms which are at stake. In terms of computations, it's also nice because this type of mathematical models really takes a few seconds to run, and so you can run them millions of times, meaning that you can use your mathematical, your in silico representation and challenge it. You can do knockout, knockdown, you can do in silico drug exposure, and then do optimization to try to understand and to optimize the therapeutics strategy. And in particular, something which is nice is that what I've written here in the brackets here is that basically you don't need to have tested every type of drugs to actually predict that they could be active. So let's say that I have drug B, drug C, drug D, and I have only data on drug A and B, but let's say that I have a target of drug D in my model, then I can still predict things about drug B even though I don't have the data. And this is good because of course we don't want to test all different possibilities in all different systems to be able to optimize things from the model to do it for us. So saying all this, it seems like everything is super nice, super positive, and that's the case. Okay, we do have some limitations here. And the main one is about the parameters. Okay, so you are going to see that we have a lot of parameters. So it's also, you can see this as a degrees of freedom. And because we have lots of parameters, we also have to be careful in estimating those parameters. Because if those parameters do not have realistic values, the behavior of the system could be completely unrelevant, could be really far away from the biology. And this is something that we really want to, I'm going to focus a lot on that. And you can see that basically in this type of approach, clearly the highest amount of work is in the parameter estimation. Once you have your model with the calibrated data, then you will be able to do whatever you want very quickly. Any question? Okay. I'm going to repeat the question. So the question is about what is the sense of degrees of freedom. So degrees of freedom is basically okay, no, so no, it's not different parameters, it will be more different terms. So if you have an equation like that, equation like this, you will have, for instance, different terms here, and then Ka and Ke would be degrees of freedom. And it's a way to say, okay, if I give a graphical example, sometimes you can say, okay, I want to build my arm. Okay, so my arm, I need my arm, I need one elbow, one shoulder, okay, and one wrist, okay. And so you have 3 degrees of freedom. Okay, your system can move in 3. If you say 2D, you have 3 angles basically, and basically those are degrees of freedom in a space manner. And so now the question is, okay, your arm can never go like this. Okay, so if this is the shoulder, if this is the elbow, and if this is the wrist, okay, let's say that you have the hand here. There's no way that I can, what I mean, okay. And that's exactly it. So basically, you don't want your parameter here or your angle here to go anywhere. For this particular case, you would like your angle to be around here. And what I'm saying is that if I want to model my arm, basically I need to make sure that I have the information about how those angles can be in reality. That's it. So this is exactly why you get. I don't see how this is. Okay, I don't see how this is relevant. I don't think it's relevant to us.
Because we want to overcome the difference after experimental and the from the.
No, it's not this. It's more the shape that you want to give at the. So sorry, the question was: is it related to the operators? And the answer is it's related to the shape you want to give to your. It's as if you want to draw. No, I mean I don't think it's relevant. But we can discuss later. Any other questions related to this quantitative systems pharmacology? No? Okay. So basically I was saying that you keep in mind that parameters and estimating the parameters are super important. So just to let you know about what type of data we have in real world, because here that's really something I want to stress, is we really need to go to real world data. So this is the type of data that we use in oncology. Oncology is cancer research, but this can actually be applied to many other diseases. So let's say that you start with the tumor, which is also the tissue where the disease is. We can actually characterize the tumor using what we call omics. So omics are data of large scale. So typically, you can have transcriptomics, and you have heard this type of thing. Transcriptomics would be in the order of 20,000 genes. The data we have. So as you can see, we don't want to model 20,000 proteins. We don't want to have a model of 20,000 proteins. We can have plenty of different data. So this is like expression of genes and proteins, so the targets. But then it can go a bit more functionally. For instance, you can apply that value to your system. And as you can see, this is really multi-scale. So here I put it is static. And here it's time dependent. You can do this, but over time. For instance, I put my drug at time t=0, and then I look at some proteins or whatever I want, some concentrations as well. And here, this is important to say that basically all cells will not be equal, may not be identical. And this is where I want to take into account the heterogeneity in between the cells. So basically, this is where the single cell data is important. Maybe you have heard of these new techniques that allows to measure plenty of different biological amounts or quantities in single cells, whereas before we had to analyze millions of cells all together. And then we want to go at the level of the whole body. So we can have, as I was saying, the patient as a start. For instance, we are interested in the PK, we will go to the liver pharmacogenomics or the polymorphisms. And then we want to integrate everything. So that's typically the way we want to go. So we integrate the patient with the disease tissues. Okay, so this being said, so the idea now is to guide you step by step to a QSP pipeline, so quantitative systems pharmacology pipeline. So how do we do quantitative systems pharmacology? So basically there is a first step about model design, and then once we have the model, we can use it for this particular case, definitely for drug combination optimization. So I will try to guide you and to explain all different parts. And then I will show you how we have done this in the real world. So the first part is about the model design. So that's here. So typically, the model can look at that. So you can have intracellular networks like this. So you may have the drug that will enter the cells, and then it will be, for instance, deactivated or transformed to some different species. And then the drug will target some genes that will then activate or deactivate or inhibit some other proteins. And all this will change the behavior of the cells and can be integrated in mathematical models of the dynamics of the cell population. So we are mostly interested in general about proliferation of the cells and how the cells divide and so on. So and also how the cell die. Okay. So in terms of mathematics, so you basically have three laws. The first law is the law of mass action, and this applies whenever you have a passive reaction. Sorry. So this is an example. I'm going to show, probably first I will introduce the law of mass action. So let's say that you have a reaction like this. So X, Y, and Z are concentrations of proteins, concentrations inside the cell. And basically, if you want to model X plus Y becomes Z, so let's say that you have some protein X plus Y that reacts, and then that becomes some product Z. Then the reaction rate will be K times the concentration of X times the concentration of Y, K being the parameter, the rate constant. And then the ODE system can be written like this, where X and Y disappears, so they will have a minus term. And Z, of course, has a positive term because Z appears. So this is the typical law that is used. And maybe I can draw your attention on two specific cases. So the first one is whenever you have a species X that is actually created from nothing in the system. Let's say that you have a continuous source, for instance. Okay, you have a source or something that is continuously coming into the system. You will use the zero order reaction, and that's just K0 times X. Sorry, K0. So K0 is just a constant. So I will write that. Okay, so let's say that for some reasons you have a source that will produce some X at some rate K0. Then so the zero order term would just be d of X equal dt equal K0. And on the same in the same way, basically, if you have X that actually gives rise to something by itself, so you have a spontaneous modification of X, for instance. So this is just K1. So if you have, for instance, X will give rise to something at the rate K1, then X will disappear at the rate K1 times X. And this is typically the case when you have in the cells, proteins, they are created and then degraded like continuously over time. And this type of kinetics, first order kinetics, is typically typically what happens when the protein is degraded. This is how we model the degradation of X over time in a cell. Okay, so now it's a small problem for you to do it by yourself alone when you are done. So this is actually quite easy. So now imagine that you have a reaction rate that you know what, before that I just want to maybe to give you an example. Maybe a simple example about blood cross-section. Okay, I'm going to draw a simple reaction network. So you basically have three reactions. So you have the prediction of X with rate K1. Then you have a reaction that creates Z from 1 molecule of X and 2 molecule of Y at rate K2, and then you have the degradation of Z at rate K3. Anybody wants to come and write the equations? Maybe you dare. No? Nobody? Okay, maybe let's go step by step again. So the idea is to first write the equation of X. So X appears in reaction 1 and reaction 2. Okay? Let's do this. Okay. Who's talking? Can you raise it? Somebody said the right way. Sorry, yeah? So I'm asking the rate of this reaction. Okay, and then the rate for this reaction is other. Yeah, that's minus because X is disappearing. K2, yes, that's here. Y and? Yeah, Y squared. Probably you have seen that there is 2y, and this is where the 2 is coming from. And if you are not convinced about this, you can also write 2 as X plus Y1 plus Y2 gives Z. And then you just replace that would be Y1, Y2, and then you just test Y1 equal Y2, and you get that. This is just a trick. If you are not completely convinced about this square. Okay, let's continue. So now we have Y. So Y is only in reaction 2. So is it going to be plus or minus? I can't hear you, I'm sorry. Anybody? Minus, okay. And then K2, yes? Exactly. So that's exactly that. That's the same rate. So that's the same reaction. And then for Z, okay, let's start with reaction 2. So here for reaction 2, that is a product separated, so it's going to be a plus sign, okay? And here we already have the rate, that's this one, it's the same, K2x y squared. And then we have that one, which is degradation. Yeah, minus K3. Okay, as you can see, that's straightforward, right? And that's your system. Okay, and now if you want to continue this alone, you can go and write the equation. I'll prove actually that the equations here correspond to the reaction which And also, I also recommend this book. I mean, if you want to know a bit more about mass action kinetics, this book is actually quite nice. Okay, so that's it for the law of mass action. So now let's move to the second one, which is so this is a typical example. Second one is mechanism. So mechanism is for this type of reactions where you have an enzyme that catalyzes the reaction. So let's say that you have E, which is the enzyme. And basically, the presence of E will speed up dramatically the reaction from A to B. And this, we will see that this term now have actually two parameters, Vmax and Km. So let's go in more details about this. So here, so this is the same reaction here, written a bit differently. So S is the substrate, so the initial thing that you have in your cell. E is the enzyme, and P is the product. And actually what is happening, like the real world, what is really happening, is that S binds to the enzyme, the substrate binds to the enzyme, and you have a complex which is SE. And then SE becomes PE, so basically the enzyme will favor the modification of S into P. So that's here. And then E will just detach, go away, dissociate from P, and you will get P at the end. So we know from the literature that basically the reaction in the middle, so SE gives rise to PE, is actually very rapid, very fast. So this one we will completely ignore it. We will say that it actually doesn't happen. And we will stick to this scheme. So substrate plus enzyme will give rise to the complex substrate and enzyme attached that will then give rise to the product. Let's write the equations using the law of mass action, because now we can use this law because we know it. So for instance, if I want to write the equation for P, so P is produced from the complex SE at the rate K1. So what would be the term here? Plus K1 SE. Okay, so whenever I put brackets, it means concentrations. And I should put probably here. Okay, this means concentrations. Okay, and if I want to write the equation for SE, and now here comes the trick, and I'm going to go to the next slide. So there are two things. The first thing is that we are going to assume that there is a constant total amount of E plus SE, because we know that the enzyme at the end is not consumed. Okay, it's not changed, it's not modified by the reaction. It's here, it's happening, but it's not consumed. It's not changed, it's not degraded, nothing. So we have this first law, which I'm going to use here. E plus SE equals some constant, E0, which is the total amount. Okay, that's the total amount of enzyme. So that's the first thing. And the second thing that we are going to say, wait, we know that those two reactions, they go way faster as compared to this one. Okay? In terms of speed, this one will be really, really fast, and this one will be slow. So, because of that, because of this change, this difference in speed, we are going to say, well, we are going to assume that this is at the steady state level. So in other words, we are going to say that this is equal to 0. So this is called the quasi-steady state assumption. It's also called the rapid equilibrium assumption here. So the quasi-steady state assumption, or the rapid equilibrium and this is what you get here in the second equation. Basically you get that this equal to 0, and then you can just use that and put it here. So this is the third line. Quite sure. So this is saying that the two first reactions are super rapid and they are at equilibrium, so their rates are equal. That's here. And then you replace E by E0 minus SE using this conservation law. Yes, sometimes this one is called conservation law. Maybe I haven't said that. Conservation law. So, and basically when you are at the third line here, you just have to rewrite things to get the rate here of appearance of creation of P. And this is what you get here. V0 times S over K plus S. And K is actually the ratio K off over K on, and V0 includes K1. And just to K1 and V0 I'm going to say. And to show you how it goes, so this rate, so it looks like this. So on the x-axis I have the substrate, and on the y-axis I have the rate. I'm going to draw them. So if I want to draw x with the rate is V0x over K plus S. Basically, so what you want to see first is that you have here like a Vmax value that is the sup of M, that is equal to V0. And then your curve goes to V0. The derivative here is always positive, V0. And if you go to half V0 here, you will get K here. So that's what is written in M minus 1 V0 divided by 2, you will get K. So and depending on your parameters, so of course the V0 will move up and down the asymptote here, and the K will change the shape here. If I draw this for a larger K, I will have something that will go less sharply to this A2, less sharply towards S2. So, and as you can see here, for this type of reactions, so we have 2 parameters, so 2 degrees of freedom, so maybe related to your questions. So basically, if we just draw this same type of graph, but now for the load intersection, the rate is just proportional to S and the substrate, so that's just Ks. Okay? So for instance, for first order. So that's something which is a straight line, and that's the shape of your rate, and you're on 1 degree of freedom. And here your shape is more complicated, and you have 2 degrees of freedom. And if your biology is really like that, of course you don't want to have like a 3rd degree of freedom, because then you will have to have plenty of data to actually set it so that it's close to this curve. This is basically something that you don't want to do because the data, it's not free, and you don't want to ask for extra data. And this is called over-parameterization. But we'll talk about this later. Any questions related to Michaelis-Menten? No? Okay, let's go to very briefly to another type of reactions which are completely related to Michaelis-Menten. So it's called the Goldbetter-Kochman kinetics. So actually, Albert Goldbetter is a famous mathematician, actually biochemist, he was trained as a biochemist in Belgium at the Université Libre de Bruxelles. And he has worked with his colleague Kochman, I don't know his first name, about this type of reactions. So we are again looking at a substrate S and a product P, but now we have we have basically a 2-way reactions. So S is transformed into P through the action, the enzymatic activity of K, and P is transformed into S through the enzymatic activity of pH. So that's here. So in terms of biology, the first one is called phosphorylation, and the other one is called dephosphorylation. And here we can actually write the equation about of this reaction network. So assuming that you have a constant amount of S and P, okay, you assume that S and P do not appear and disappear, they are here and they stay here. So you have conservation loop for S and P. And then you can have your state variables would be the relative amount of S with respect to the total concentration and of P respectively. So Y would be the P concentration over the total amount. And basically, as you can see here, you have a Michaelis-Menten term for the phosphorylation, and also here a Michaelis-Menten term. Here the VA is now the V non, and KA is K, and same here. So what is I'm not going probably into the details, but what I want to show is if you draw the 2 terms, so that's maybe I'll go back. So if you take this term and that term and you just draw them, so you get those 2 curves. So here they are called F1 and F2. And this is drawn for VA equal VI and KA equal KI equal 0.04. This is written here. And basically here, we see that they cross at 1 and at a single point, which is here. So and when they cross, F is equal to 0, and this is where we get the equilibrium, right? So here you can say, or you can see actually, that there is only one equilibrium that will depend on the value lambda, because here K and Ki are considered as fixed, and you have this value lambda which is defined as VA over VI. And basically when you, I'm not going to demonstrate that, but basically you can compute the equilibrium, which is that, X star, which depends on lambda, assuming that Ki and Ka are fixed. So you can look at the formula above, and when you plot it in terms of lambda, so this is X star in terms of lambda, you can see this type of behavior. Depending on the parameter lambda, the value of X star can be very different. So if I draw this curve, is just with respect to some parameter lambda, you have the equilibrium X star, and you have a steep behavior like this. And it means that basically if you change a bit lambda, you may change greatly the value of X star. For instance, if you are here, for value lambda 1, your X star will be close to 0. And if you slightly change your lambda 1 into lambda 2 with a small with a small perturbation epsilon, then your X star will be completely different. Okay, will be closer to the maximum. And this is called ultra sensitivity. So basically, your system is ultra sensitive to the parameter lambda, because if you change the parameter lambda of a really small amount, if you apply a small perturbation of your parameter, you will have a great impact on your system. Ultra sensitivity. So the first law we saw was the law of mass action, second law was the mechanism then, and the third one, which is related to transport, is given by the fixed first law, and it's to model the transport between two compartments. So let's say that you have, for instance, the extracellular space here and the intracellular medium here, and you have the cell membrane here, and you want to model the transport between the two compartments. Well, it's actually quite simple. So basically, the first fixed law says that the transport is proportional to the concentration. So if we focus on the K in, so on the reaction from the left to the right, so that's for instance this term here. So the quantity that will enter here as so here A are concentrations, when you should listen that, A are concentrations. And basically, so when you want to write the rate of this arrow, you get that, which is just proportional to the concentration that is outside of your cell membrane. So the K in will depend on several things, including membrane permeability, of course. If your membrane is thicker or more permeable, the parameter will change, and it may also depend on other things like temperature and pressure, and of course it depends on the contact surface, so the surface that shares basically the two compartments. Okay? If you have a large contact surface in between the two compartments, you will have a higher probability to pass through this surface. That's it. That's it for the fixed law. So quite simple, I guess. And with this, I will finish the first part, which was about model design. So as you can see, we are really relying on few mathematical laws for model design. Of course, there are others, but at least with these ones, you can really build plenty of mathematical models. So now, once you have your mathematical model and your equations, you want to estimate your parameters. And as I was saying, this is really important. And this is where you want to collect plenty of different data with different dimensions, different types. So here I have, for instance, shown the time, because you can have time-dependent data, and you can also have dose-dependent data for different doses of the drug, and then you will have data for different species or different quantities. So here I put drug concentrations, protein concentrations. For instance, in power I'm interested in the target concentration. And also you can have data about the number of cells which survive the treatment. Okay, and now I want to talk about how you integrate this data to estimate your parameters. So the typical way you want to do that is to use least square approaches. So what we do is we want to minimize the distance between your data and the model. So you have your model, and the model is f of t of today are the parameters, and basically what you want to minimize is this quantity. So that's the sum for different data points. So given at the time ti, you have the value of the data that is di for different i's, to that number small n, and then you have this L2 norm that you want to minimize. So this is called a cost function or loss. And this is the typical least square. And you can also upgrade this a bit if you have other things that you want to add. For instance, you can say, so you can add term here to the cost function to minimize. And for instance, this term can be the lasso regularization, which is in this. So this is the L1 norm of the parameters, theta. And this is just to ensure what we call sparsity. Sparsity is when you want the minimum number of parameters to be equal to a non-zero value. So basically you want as many parameters as possible to be equal to 0. Let's say that you think that you have a mathematical model that is too large, for instance, or if you want to investigate the most important ones, you would include this sparsity regularization, the lasso regularization, L1 here, to force the system to put as many parameters as possible to 0. This is called sparsity. The second regularization that is well known is the ridge regularization. Is when for some reasons you want to decrease or make sure that your parameters are not getting too high. In that case, you would use the L2 norm of the parameter vector. So this is to say, okay, I don't want my vectors to be too large, my parameters to be too large. And the third type is something basically you put whatever you want. So it's, let's say I have some biological constraints, something that is not in my data, but that I want to put here, something like qualitative constraints, for instance. So for instance, let's say that I know that okay, I'm going to speak louder. So let's say that, for instance, I want some variables to be greater than the other one. Let's say that I have x and y. I'm going to write it. Let's say I want, for instance, x greater than y, and I can put this in my constraints in this lambda. minimization algorithm. So for this, we have decided to use another type of algorithm which are relying on stochasticity. And the one I would like to highlight is the CIMPA, so the covariance matrix evolutionary strategy here. And I really encourage you to go on the website of Nicolas Hansen, who actually derived this very nice algorithm, and he's still updating the algorithm every day. And so it's not fast, I mean, as you know, as compared to the brain MSF, it's way more computationally expensive, but it's clearly handled better this type of situation, and this is always the case. I mean, when you have a complex, or let's say just a real world model with data, biological data, you always get very complicated shapes of your cost function. So this is why you need a robust minimization algorithm to be able to handle this type of problem. And the third thing which is important is that remember that in my cost function here, I said you can put whatever you want in the lambda C, including things which are not continuous. So you can actually introduce discontinuities. For instance, if I say if my constraint is not fulfilled, then I make my loss to explode. This is something that we can actually put. Okay? If you are sure, 100% sure that the constraints need to be fulfilled, you can just say if it's not fulfilled, put a very, very large value to my cost function. And if you do that, you will have cost functions that will explode for some values of the parameters, and hence you will have a cost function that is discontinuous, that is not continuous anymore. And this, you need to be able to handle that, and CMAS is actually able to handle this type of discontinuities. Okay, so now I guess you understand that I advertise this algorithm because I really think, and I actually, in my everyday life, I really see that it's actually working very well. Well, there are other ones. I mean, there are plenty of them, but if you want to have a good one, I mean, I would recommend this one. Okay, so now the first vector